Alright guys, let's get started. Today we will finish chapter number 7 and I will also give you the homework questions of this chapter, chapter number 7, after today's class. The due day for the homework is also 1 week. So today is Friday and next Friday is gonna be the due day for chapter 7's homework. Okay. Alright, so last time we talked about how to use first order and second order differential circuits to build filters, and we have introduced 3 kinds of filters. They are low pass, high pass, and band pass filters, right? At the beginning of today's class, let's quickly go through, do a quick review about these 3 types of filters, and then we will introduce the last type, yes, which is the band reject filter. Okay, all right. So to build a low pass filter, we can use a RC circuit, right? In this RC circuit, the input voltage is, or the input signal is defined as the source voltage source, and the output voltage or the output signal is defined as the voltage across the capacitor, right? So this is RC circuit, and we said the reason why we can call this circuit as a low pass filter is because the plot of magnitude of the transfer function with respect to omega c, which is the frequency, follows this shape. When omega is below omega 0, which is defined as the cutoff frequency. When the frequency omega is below omega 0, the magnitude of this filter is above 1 over square root of 2, right? Which is defined as high magnitude, right? And when the frequency is above cutoff frequency, the magnitude is below 1 over square root of 2, which is defined as the low magnitude, or the low magnitude. So as I mentioned the last time, a low pass filter can be imagined as a switch. When the input signal has a low frequency component, then this switch will be opened, right? Because the magnitude for low frequency component is high. And for high frequency components, such as if the input signal has the frequency is above the cutoff frequency, then the low pass filter will reject, which can be imagined as an open switch, right, or an off switch. Right, so that's the mechanism and the plot of the low pass filter. And also we have introduced high pass filter. A high pass filter shares a same circuit with the low pass filter. We can also use an RC circuit to build a high pass filter, but the difference is right now the output voltage is across the resistor instead of the capacitor, right? And the plot of magnitude of the transfer function of this circuit is the opposite shape with the low pass filter, which can be presented in this way, right? When the cutoff frequency, when the input signal has the frequency which is below the cutoff frequency, then as you can see, the magnitude is small, right? Is below 1 over square root of 2. And when the input signal has the frequency component above the cutoff frequency, right? Then the magnitude is high, which uh, which means the high pass filter will accept high frequency component, right? Right. So those are two types of filters that are built based on first order differential circuit RC circuits, and we also introduced band pass filter. Band pass filter is built based on a second order differential circuit, which has three components. An inductor L, capacitor C, and a resistor R. The input signal is also defined as the voltage source, and the output signal is the voltage across the resistor, V out. Okay. And also last time I give you the plot of the magnitude of the bandpass filter, right, with respect to omega t. And this plot is similar to a bell-shaped curve. It has a peak point, omega 0, which is defined as the central frequency. Omega 0 for bandpass filter equals to 1 over square root of LC, right? And also it has two cutoff frequencies. They are defined as omega low and omega high. Omega low is called low cutoff frequency, and omega high is called the high cutoff frequency. We have two expressions to represent these two variables. Omega low can be calculated as minus R over L plus square root of R over L square plus 4 omega 0 square, okay, divided by 2. And omega high equals to positive R over L plus square root of R over L square plus 4 omega 0 square divided by 2. Okay. Right, so those are three type of filters that we introduced last time in the last class. Today we're going to introduce the last type of the filter, which is band reject filter or band stop filter. Band stop or band reject filter shares a same circuit configuration with the band pass filter. It is built by a second order differential equation, but the difference between the band pass filter and band reject filter is the location of the output signal. For band stop or band reject filter, the output signal is the voltage across the inductor plus the voltage across the capacitor. Okay, the voltage across these two components. The input signal is still defined as the voltage source. Okay, and the plot of the band reject or band stop filter is very similar to the band pass filter. You just need to flip the band pass filter, and the result is the band stop filter. And also we can define three variables: omega 0, low cutoff frequency, and high cutoff frequency, right? the representation or the expressions of these three variables are same with these three expressions. There's one thing I want to mention for these three variables. All these variables are presented in the unit of radian per second. Okay, because sometimes the question will tell you the central frequency of a bandpass filter or a band reject filter is 500 hertz, for instance. Okay, then you cannot directly say f0 equals to 1 over square root of LC equals to 500 hertz, because 1 over LC, the result of this formula, is in the unit of radian per second. It's not in the unit of hertz. Okay, so if the question gives you a variable in the unit of hertz, you need to convert this variable to the unit in radian per second. For this example, you need to find what's the corresponding frequency in radian per second of 500 hertz, and that will be omega 0 equals to 2 pi f0 equals to 2 pi times 500 radian per second. Okay, and then after you have 2 pi times 500 radian per second, this number, you can say that equals to 1 over square root of LC. Okay, this is correct, but this is not. Alright, so these are four filters that we introduced in this class, and there are still two important concepts are related. There are still two important concepts related with bandpass and bandstop filters that we need to introduce. They are quality factors. Quality factor Q and bandwidth. BW. Okay. The quality factor Q is defined as omega 0 divided by bandwidth. Okay. And bandwidth is defined as omega high minus omega low. So let me explain how to calculate bandwidth and quality factor. To calculate bandwidth, we just need to plug in the expression of omega high and omega low into this formula. In other words, we just need to subtract these two expressions, and the result gonna be what? Gonna be 2R over L, right? Because they have similar structure, and the result of this subtraction is 2R over L. I'm sorry, that should be R over L, right? Because when you minus these two expressions, this one and this one, the result is R over L divided by 2 minus R over L divided by 2, and that should be R over L. Okay. So that's how we calculate the bandwidth. After we have the bandwidth, we can find what's the quality factor Q. Q equals to omega 0 divided by bandwidth, and omega 0 equals to 1 over square root of LC times L over R, right? Which equals to, we can modify the second term a little bit, and that is L square root of L square over R square, right? And that equals to square root of 1 over LC times L square over R square, which equals to L over C square root times 1 over R square, which equals to 1 over R times square root of LC, correct? So that's the quality factor. Alright, so let's see an example of using, let's see why we need to define these two concepts, because these two concepts will describe the characteristic of a bandpass or a bandstop filter. For instance, if I give you a quality factor, then you can you can have some basic information about this bandpass or band reject filter based on the value of the quality factor. For instance, let me give you 3 plots. Okay. So that's the first one. That's the second one. And that's the third one. These 3 plots, these 3 band pass filters, they have a same central frequency, but they have different quality factors. Which one has the highest quality factor? 1, 2, 3. Okay. The answer should be we can analyze why we have 3 different shapes. Because they have different bandwidths, right? For the first one, the first bandpass filter has a narrow and tall shape, which means the bandwidth of this bandpass filter is small. And for the third one, the bandwidth is wide, right? Because the shape, we can observe the bandwidth from the shape of the third bandpass filter. It has a very short and very wide shape, which means the bandwidth will also be very wide. And let's compare the first one and the third one. For the first one, the quality factor will be what? Will be larger than the quality factor of the third one, right? Because quality factor equals to central frequency divided by bandwidth. And they have the same bandwidth. They have the same central frequency. The larger the bandwidth, the smaller the quality factor. And the bandwidth of the first filter is smaller than the bandwidth of the third filter, which means the first filter's quality factor is larger than the third one, correct? Right, so based on the quality factor, we can have some basic information about the shape of the bandpass filter. The higher the quality factor, the more narrow and tall of the filter it is. The smaller the quality factor, the wider and shorter of the bandpass filter it is, right? And this principle also applies on band reject filters, right? Because they have these 2 filters typically are basically are the same. They just you just need to flip the plot of a bandpass filter, and you will have a bandstop filter. Okay. Right. So let's see an example of using those expressions to do an actual calculation. Alright, so that's the circuit we have, and based on this circuit configuration, we can identify this is a bandpass filter, right? Because this circuit configuration is identical with bandpass filter. Alright, so in this question, we need to find central frequency omega 0, low cutoff frequency omega low, and high cutoff frequency omega high, and the bandwidth BW. Okay. And also we know the inductance, capacitance, and resistance. So from this information, we can use the formula of central frequency, that is omega 0 equals to 1 over square root of LC. So we can just plug in the inductance and the capacitance. Inductance is 1 Henry. Capacitance is 1 microfarad. We need to convert 1 microfarad to farad, which is 1 times 10 to the power of minus 6. Right? The result is 1000 radian per second. Okay. Right after we have central frequency, we can calculate what is the bandwidth. Bandwidth equals to R over L, right? And that equals to 1 kilo ohms, that is 1 times 10 to the power of 3 ohms, divided by 1 Henry, which equals to 1000 radian per second. Right after we have the central frequency and the bandwidth, we can calculate what is the low pass filter and what is the low cutoff frequency and the high cutoff frequency, right? Because if this is the central frequency, the bandwidth is the distance from the low cutoff frequency and high cutoff frequency. If I tell you the central frequency is 1000 radian per second, the bandwidth is 1000. It's also 1000 radian per second. Then from here to here, the distance is 500 radian per second, and the same thing. The distance from central frequency to high cutoff frequency is also 500 radian per second. Right. So based on this information, we can do the calculation. That's right. That's right. So we can do the calculation. So the low cutoff frequency, omega LO equals to 500, which is central frequency. That's 1000. I'm sorry. Minus 500 equals to 500 radian per second. And for high cutoff frequency, that equals to 1000 plus 500. That equals to 1500 radian per second, right? Alright, so that's how we calculate the central frequency, low cutoff frequency, high cutoff frequency, and bandwidth. And also you can find what's the value for quality factor Q. That will be omega 0 divided by what? Divided by bandwidth, right? Which equals to 1000 divided by 1000, which equals to 1. The quality factor is 1. Alright, so in this example, we showed how to use these formulas to calculate variables of a bandpass filter. And in this example, we're gonna learn an application of using a bandpass filter in the real world. Okay. So let's consider a situation. Everyone loves listening music, right? And when we are driving, a very convenient tool that we will use to listen music is the radio, right? And if we want to select some radio station, we just need to rotate a knob and pick our favorite radio stations. So how does a radio station select a specific radio station? As we know, there are many hundreds radio stations are transmitting signals, different signals in the air. But these signals are carried by different frequency range. So the application or the mechanism of the radio in the car is that it has a frequency selector which can be adjusted. And when you change this frequency selector, you can pick different signals in different frequency bands. So let's draw a general plot of a radio station of a radio. Okay. So it has an antenna. The antenna will receive signals in the air, and there are many different signals carried with different frequencies, such as 1.5 kilohertz, 2.0 kilohertz, 2.5 kilohertz. Okay. There are tons of signals in the air, and after the signal are picked by the antenna, it will pass a bandpass filter. Okay, the bandpass filter actually is the frequency selector. And after the signal pass or goes through a bandpass filter, the next module is a signal processing module, which will further reduce the noise from the signal you picked. Let's say we want to listen the signal on 2.5 kilohertz frequency. Okay. And after 2.5 kilohertz signal goes through, pass through the signal processing module, the signal will be transmitted to a speaker, and we can listen the pure signal from this radio station, right? Right, so that's the general diagram of how a radio works. And in this class, in this example, I want to focus on this bandpass filter, right? Because this is related to our topic. After the signal, before the signal pass through a bandpass filter, it has different frequency components. But after it passes a bandpass filter, the only signal can survive is 2.5 kilohertz, which means the bandpass filter has a central frequency at 2.5 kilohertz, right? And at this frequency component, the magnitude is high, is 1, and below the low cutoff frequency and the high cutoff frequency, the magnitude is very small, which means those signals will be rejected. And only in this frequency range, the signal can be passed. And an ideal bandpass filter should have a very large quality factor, right? Because we don't want to pick any other signals at different frequency range. We just want signal at 2.5 kilohertz, which means we want the bandwidth of this bandpass filter. The bandwidth should be very small. Okay. Then we will have a very precise signal selector, frequency selector. Right, so how to design a frequency selector or a bandpass filter in this example, right? So let's assume the signal we want to pick is at 1200 kilohertz. Okay, that's the signal we want to pick. And if I tell you the inductance of bandpass filter is 100 microhenry. Can you tell me what are other components values, such as what are capacitance, resistance? So to solve this problem, we need to use the formulas that we defined before. Since we already know the central frequency is 1200 kilohertz, the first thing we can do is we need to find what's the corresponding central frequency in the unit of radian per second, right? So f0 equals to 2 pi times omega 0 equals to 2 pi f0 equals to 2 pi times 1200 times 10 to the power of 3 radian per second, right? And after we have this information, we can find what is the production of LC, because omega 0 equals to 1 over square root of LC, right? And we can plug in omega 0, the inductance 100 microhenry. But remember, when you use 100 microhenry, you need to convert this variable to the base unit, which is 100 times 10 to the power of minus 6 Henry, right? Plug in these two values, and we got 2 times pi times 1200 times 10 to the power of 3 equals to 1 over square root of 100 times 10 to the power of minus 6 times c. And as you can see, there's only one variable in this equation. So we can find what's the capacitance. C equals to 176 picofarad. Okay. Alright, after we have the capacitance C, we can find the bandwidth, BW. BW equals to R over L. And here we have some selections. We need to select a bandwidth, right? We need to define a bandwidth. As I mentioned before, the bandwidth should be very small because we want to precisely pick the frequency we want. So let's see if the bandwidth equals to, if the bandwidth equals to 100 kilohertz. Okay, let's just assume the bandwidth equals to 100 kilohertz. Then the corresponding resistance equals to 100 times 10 to the power of 3 equals to R over 100 times 10 to the power of minus 6, right? So R equals to 100 times 10 to the power of 3 times 100 times 10 to the power of minus 6, which equals to 10 ohms, right? So that's the resistance we need. And for this bandpass filter, we can do a plot, right? The central frequency we need is at 1200 kilohertz. The bandwidth is 100 kilohertz. So the low cutoff frequency is going to be 1150. And the high cutoff frequency is at 1250. The unit are kilohertz. But I made a mistake here. the mistake I made is right here. The bandwidth equals to 100 kilohertz, but 100 kilohertz is not equals to R over L, right? Because this is not in the unit of radian per second. Only 2 pi times 100 times 10 to the power 3 equals to R over L, right? But for the calculation convenient, let's just assume the bandwidth right now equals to 100. No, let's keep this unit, and R has a different value. This is gonna be 2 pi times 100 times 10 to the power 3, and this is gonna be 2 pi times this term, right? And the final result is gonna be 10 times 2 pi ohms. Okay. Right, so let's finish this plot. At the central frequency, the magnitude should be 1. And at the low cutoff and high cutoff frequencies, the magnitude should be 1 over square root of 2. So that's the plot we have for this band-pass filter. And we can calculate the quality factor of this bandpass filter. That equals to omega 0 divided by the bandwidth. Omega 0 equals to 1200 kilohertz divided by 100 kilohertz, which equals to 12. Okay, and let's take another guess, or let's take another assumption. Let's assume the bandwidth equals to, this time let's pick a much smaller bandwidth, which only has 1 kilohertz. Okay. Then we can find the corresponding resistance. If the bandwidth equals to 1 kilohertz, then 1 kilohertz, 1 times 10 to the power 3 times 2 pi equals to R over L. And R equals to 1 times 10 to the power 3 times 2 pi times 100 times 10 to the power minus 6, which equals to 2 pi times 100 times 10 to the power minus 3, which equals to 0.2 pi. Right. The unit is ohms. Alright, after we find the resistance, we can do another plot. This time the central frequency is still at 1200 kilohertz. But since the bandwidth is just 1 kilohertz, so this time the bandpass filter is going to be very narrow and tall. And the quality factor, omega 0 over bandwidth, will be 1200 kilohertz divided by 1 kilohertz, which is 1200, right? So this time the quality factor is much larger than the previous one if you compare these two numbers. Alright, so that's all materials, that's the all content about this chapter. In this chapter, we introduced 4 different types of filters, and we introduced how to build these 4 types of filters by using first order differential equations. And second order differential equations, right? And also we introduce the applications of the bandpass filter in the AM radios, right? We can use a bandpass filter to pick our favorite radio stations at different frequency bands. And after today's class, I will post the homework of this chapter. You guys have 1 week to finish the homework. And by the way, if you need some homework extensions, such as if you couldn't finish the homework before the due date, just give me a message, give me an email, and explain your reason for the extension. Then I will give you another week to finish the homework. Okay. And also, if you have any questions regarding the homework questions or lectures, examples, please let me know. Okay. All right. I'll see you guys next time.